So Hamish Fraser trained in general medicine, cardiology, and knowledge-based systems at Edinburgh University, and in clinical decision making at MIT. His work has led to the migration of medical informatics tools and expertise from high-income countries to some of the most challenging environments in low-income countries. Director of Informatics at the leading healthcare NGO Partners in Health, co-founded and co-leads Open MRS, an open source EMR project. He was also an assistant professor of medicine at Harvard Medical School from 2006 to 15. He teaches courses in global e-health at Leeds University, Edinburgh University, and MIT, and recently co-authored a textbook in this field. His main academic focus is in the evaluation of medical information systems, particularly in LMICs, and understanding the impact of information and communications on quality of healthcare worldwide. So Hamish, we're delighted to have you with us this morning, and we look forward to hearing from you about benefits of computerable knowledge in low and middle income countries. Thank you, Hamish.
And do I share my slides then?
Please, if that's okay.
Yep, I can do that.
Thanks.
That's correct.
Yeah.
Okay, can you see that?
Yeah, just needs to go into presenter mode.
Yep. Okay.
Thanks.
So apologies for the timing thing here. So what I'm going to talk about is some work that we've been doing for the last 4 years in Kenya, in Eldoret, with the AMPAP project. And this is really looking at how can we develop more advanced computable biomedical objects based upon machine learning models, and not only to implement them in open source systems with open standards, but also to do rigorous impact evaluation of the systems as well. So very briefly, HIV/AIDS, I'm sure many of you know about this, but one of the key things about HIV is that it has been a huge scourge, which has been successfully managed in many cases with antiviral therapy, with triple therapy. But although this works extremely well, many people have been able to live long life with it, there is a very strict requirement for compliance with medication. So patients who miss even a couple of drugs doses within a month can start to run into problems. So it's quite a strict regimen, and people who are lost to follow-up, which is a key problem, can be at risk. So in HIV care, you have a whole continuum from diagnosing, screening people for HIV, diagnosing the patient, linking them to a care process, and then maintaining them in care and maintaining them on treatment and responding to any particular complications and problems. And what we see is that discontinuation of care and loss to follow-up impacts more than a third of all patients overall. And this is a high problem in the US as well, but it's a particularly challenging problem in somewhere like East Africa, like in Kenya. And there are a number of ways in which you can support patients to ensure they take treatment. This is actually from Partners in Health, providing a direct observed therapy every day. Of course, most programs can't afford to do that for everyone. And so there are various ways you can handle that, including more frequent clinic visits, providing more frequent testing of viral load, but there's a cost attached to that, and increasing patient support in other ways. But there are obviously limited resources and staff available to do this. So EHRs can be very valuable and were one of the real critical components of scaling up HIV treatment in low-income countries over the last 20 years. And so by tracking patients and ensuring that their treatment is stable, that they aren't having complications, this becomes a critical part of actually maintaining care. So retention is managed really by successive clinic visits, by supporting the patients, ensuring that they come for pick up their medications. And there are a number of interventions that have been used to try and improve that, particularly alerts and reminders to warn if patients are not showing up for visits, or if they have not picked up the medications and so on. So what we were looking at was how could we improve adherence at the AMPAF project, which has more than 200,000 patients that have been in care over the years, and where you really need to find ways of improving the compliance without using a lot of extra resources. And so we knew from Tom Maluch's work in a large clinical trial a few years ago that alerts to warn about, for example, abnormal CD4 counts could be effective in helping to respond to patients who were failing treatment. And recently, AI and particularly machine learning techniques have been looked at as a potential to identify high-risk patients before they stop treatment. And a number of projects have tried to use this. Um, AMPATH has had this very large data set going back to the beginning of OpenMRS in 2006. And we were able to build on the long-standing experience of using OpenMRS, the open source medical record system that we developed, to support both the data collection, the development of the models, and the deployment of the models as well. So the hypothesis was really that health facilities utilizing data-driven clinical decision support systems will show improvement in process and outcomes of HIV care compared to control facilities. OpenMRS is an open source medical record system. It's designed based upon the original design of the Regner Street Medical Record System in the US. As a concept dictionary for data storage. It's been open source since 2007 and is a very modular architecture, which allows you to add new functionality. And it's supported by programmers all over the world and is used in something like 65 countries, nearly 7,000 health facilities, and probably more than 20 million patients, with very strong focus within the US PEPFAR HIV program, which we'll come back to. It was started by a team at Reckon Street and Ampath, colleagues Paul Bjorndich and Burke Mamlin, Chris Siebrecht, and also Bill Tierney. The Ampath medical record system, as I said, started in 2006, but at the same time as we started working in Rwanda, and also Chris Siebrecht's team in South Africa were deploying a system based on the same EHR. So continuous use in 2006 with over 200,000 patients at Ampath. And 2020, a new cloud-based point-of-care interface with much more advanced clinical decision support systems was started, hosted at Moi University, and accessible by about 100 health facilities in Western Kenya. And so one of the key parts of OpenMRS is what we call the SEAL Concept Dictionary. This is work that Andy Cantor has led over many years, and it provides really detailed mapping from tens of thousands of concepts in OpenMRS to all standard coding systems, including ICD-10 and 11, SNOMED, LOINC, and others. And these are partly from Andy's work at IMO, using basically pro bono support for these kind of mappings. The modular architecture is also unusual because instead of just having certain components that are modules, really all the key functionality in OpenMRS can be built with separate modules to be put together into one system with just really the database and the APIs in the back end. We've also been working to provide good support for FHIR. And so Ian Backer, who's been working for me for a number of years at Brown University, is also a technical lead now for OpenMRS through University of Washington. And he and colleagues, and particularly Ray Falconberry and Jan Flowers and others, have worked to really support FHIR and to use that in a number of countries, particularly in West Africa, for linking for lab systems. So we're trying to really ensure that all the standards are really well supported. So one of the things we want to do was, of course, to predict missed clinics visits. And so these are some examples of different people's journeys here. And the color coding shows when the patients got into trouble. And the black marks are showing clinic visits. And so you can see there are different patterns of patients. And the idea is that we can find patterns within there that will give people an early warning that somebody is likely to miss a visit or become lost to follow up. These are some models that were developed based upon a research data set, which is exported from Ampath every 4 months with a standard set of codes. And so we're looking at the best ways we could actually predict these visits. And these models are looking at different factors within a particular individual patient's results that were driving the model to actually indicate higher risk. So, for example, the patient here had a most recent delay of more than 28 days. So that was obviously a key factor. And so when we developed these models, originally we had a fairly large model with more than 50 variables, but now we have a couple of models. One is 20, one is 27 variables with RSC covariates around about 0.74. And we found that XGBoost and GBM were two successful models, but also linear models like GLM had a pretty similar result. So there's some interpretable models at the same sort of performance level. These are the key findings, the variables that we actually end up using in the model, including, importantly, whether certain data is missing which can often be an indicator that the patient is at higher risk because they don't have certain data recorded for some reason. So we then needed to deploy this model as a decision support system within the EHR as part of the day-to-day care process, of course, and really to focus on enhancing data-driven decision-making by clinicians, treatment supporters, and program managers. So we built a server architecture based on OpenMRS and also using FHIR as one of the options for exchanging data. We generate weekly lists of high-risk patients at each clinic. And then we've been working on a co-design process to build basically a clinician dashboard to support the output of the models in their decision-making. The initial results showed that with the first model, looking at all patients, there was a 40% missed visit rate or delayed visit rate, and the top 10 predicted patients was 68%. So you can see the model was effective at picking up some of the higher risk patients. We did, however, notice that in this particular model, sensitivity is relatively low at 31%. So it's not picking up a lot of the patients who are high risk, although the PPV was good. So we then validated the system with data from over 100,000 patients spanning a period from January 21 to September 2024. This being when the newer point of care interface was available. We defined it missed clinical appointment by 1 or more days. And then we also looked at, 5 different domains of data, included demographic, historical adherence, clinic settings, service utilization, and clinic indicators. And we also used a super learner ensemble model to improve the performance, although the difference isn't all that huge. The validation of the 27 particular model, we actually used over almost 5 million encounters. And that was between January the 1st and September 24. And then before we deployed the model, we reran it just on the data up until April of 2024, so a 3-month period, to see if the model which had been trained just before that, was actually fully effective and it maintained the performance on that piece. However, there were some challenges in changing from the original AMPATH research data model to actually employing the system. And you can see that these models, both the adult and pediatric, had good performance. So the way that we use the data set for research has been important for a lot of different studies on HIV care, including IDEA, which compares outcomes across different countries in Africa. But when the AMPATH medical record system point of care clinical decision support system was implemented, it needed to have a flat file data export generated every night to drive the decision support rules. So once we had the best model, we implemented in the EHR and led by Ian Backer and the programming team in Kenya, they were able to deploy that model and then test that out with the flat file data. And it may not be surprising that there was a drop in performance, though actually it went from 74% to about 54%, so not really much use. So we then had to retrain that and then went back up to a good performance again. So a great example of even within a particular EHR that deploying the system when the data was being exported in a different way can really affect the performance a lot. And some of that we think was originally because the data for the first models went back before 2021, and so there were changes in prevalences of different things, particularly loss to follow-up. So really we're interested particularly in how can we look at machine learning models to better predict loss to follow-up and also for virological failure. So if the patient's actually failing treatment, we're interested in whether they can be effectively communicated to the clinical team and do that, the staff receiving the alerts make better decisions. And then of course, do those decisions lead into better patient care? This is just a simple diagram of the system. We have the database for the OpenMRS system here. This is the point of care user interface, which normally links to that for standard data access and decision support. And then you can see we extract data, use a prediction model to generate the outcome for this patient, and then that's sent to the user interface. This is using a causal model to think about how this process works, particularly for the loss to follow-up patients. So obviously clinical data is entered, prediction model produces a probability of loss to follow-up or missed visit in this case. And then a list of patients with high probability of missed visit are displayed weekly to the treatment supporters. And then the question is, does that change their actions and behavior? And does that result in better outcomes for the patients, particularly in terms of adherence to care? So this is one of the interesting parts of the project. So as I'll discuss later, rather, there is very little actual clinical evaluation of machine learning models in low and middle income countries at the moment. And so apart from imaging-based systems, we see very little real evidence base. And a lot of people have started to deploy these kind of models for predicting missed visits, but they don't seem to have really done clinical evaluation. So here what we've done is to create a system where when the treatment supporters are calling the patients who are highest risk on the list, we track both who was called, how many phone attempts were made, whether they got through to the patient, and then what happened to that patient afterwards in terms of the phone attempt, including did they say that they would not be able to make the appointment and we could rearrange the appointment, or did they just not show up? And from what we can see here is that those people who were not contacted had a 41% misvisit rate. Um, the ones who were in the group that were contacted, the unsuccessful attempts was 36%, sorry, attendance rate. So there's 41% attendance rate, 36% attendance rate in those who were unsuccessfully contacted. But in the ones who actually were contacted, if they kept their appointment, it was 57% attendance. And in fact, because some were rescheduled, it actually could be seen as being almost 70% attendance. So a lot of operational questions about this. Um, how do we actually develop the scores? Do we pre-calculate them or try to do them at runtime? Obviously, the issue with the side of research data set versus the flat file data, derived variables, how are they actually handled in the different data sets and how does that affect the quality of the data? And also then what risk bands should be used for classification of patients in this category. So the top 10 and top 20% seem to work reasonably well for the missed visit patients, but it's not so clear what we use for viral load, for example. And then when we generate predictions, how long should they last for? Should they expire after a day or after a week? So when we looked at this question of outreach workers, first of all, we had the pre-appointment contact list. So the patient's scheduled to have an appointment and then predicted to be at a certain risk of misvisit. And so we're really looking at short-term misvisits here. And then at the appointment, when the clinician, which could be a doctor or a nurse, or a community health district health officer who has a 3-year training in medicine, they will then need to see information about both the patient's risk of missing the next visit, but also viral load predictions. And so how do we look at that information and make sure that the clinicians can actually use that in their thinking? So this is a couple of examples from the point of care system. So it's a very good system, but it's not got the most beautiful user interface. So we'll come back to that. This is the list of high-risk patients, which are given to the treatment supporters. And then this is the interface, which has a number of alerts and reminders for the clinicians. You can see this one's a little bit older, so it has COVID alerts on it. But it has, appointment 52%, 58% risk of no show for the appointment. So as part of this study, which is funded by the NIID, we wanted to really look at different levels of use of the system. So both the misvisit level, but also, of course, how can we support the clinicians in their processes? And then how do we actually look at performance, both initially in terms of functionality and usability, but also in terms of the impact on care. So following a pilot phase in 8 clinics, we've been conducting a step wedge randomized controlled trial in 63 AMPATH-supported health facilities. And the plan is to conduct a second, smaller study of the use of the dashboard for the clinicians. So currently the status here is that we started in April 24 with the RCT with 8 to 10 clinics per cohort. And the final cohort was actually enrolled in August 2025. And we had a few wee problems in January and February with PEPFAR, which led to the suspension of the randomized controlled trial. But fortunately, in terms of AMPATH and their HIV treatment program, they did receive their funding back. And although there were some long delays in getting all of the funding, for example, for the mobile phone contracts for the staff who were calling the patients, we were able to restart recruitment this summer. The final data collection for the RCT is actually expected in the next couple of weeks. And beginning of the year, when we were at 50% complete, there were over 31,000 patients in follow-up. So some just interesting results on this. We looked at the implementation of the model and for missed visits, and then we had to both train the staff and support them in actually calling the patients, but also recording clearly what was happening to the patients, and then tracking that process so we could actually evaluate the impact on their retention in care. And so as we've done this, we've actually looked at a number of different ways of trying to improve the usability of the system, and also to make sure that we keep track of all the different patients and when they're called. And so that's required quite a lot of training and support from the research team. When we looked at the missed visit prevalence, it was about 36%, and the ROC curve performance was 72%, so similar as before, PPV of 48% and NPV 81. The higher PPV than prevalence implies that relative to the random sample, we're actually flagging the higher risk patients. And highest variable importance in terms of the models was number of prior missed clinic visits in the last 3 visits, days since the last viral load, so we don't know exactly what the status of the viral load is, number of visits since enrollment, and also clinic location. And we also saw, for example, that there were 26,000 scheduled visits from September 2023 to April 24. 29% were flagged as high risk. And prior to scheduled visit, the outreach workers called 74%, and 73% of those were successfully reached. And you can see that there was a 39% return in those reached and 27% in those not reached. And those were flagged that were not called had a lower predicted risk, and so they were 38% attend. So as looking at this so more broadly, we need to think, well, how do we engage with clinicians in this process? And so we actually carried out a qualitative research study about 2 years ago where we had clinicians from AMPATH in both focus group discussions and key informant interviews. And we also did a root cause analysis study of the causes of missed visits and loss to follow-up. And through this information, we were able to then develop a strategy for how to move forward with the clinician side of things. And so in this second qualitative research study, we're just setting up to perform hopefully in the next 3 to 4 months. Again, we're recruiting the same clinician groups. Each will be shown a clinical description of the patient based upon some patients from the research data set, but obviously de-identified. They'll be asked their assessment of the risk of missed visit and what action they might take for virologic failure before and after reviewing different UI designs. So we're going to look at 2 or 3 different designs and look at what information displays and also what supporting information is most useful. And then, of course, they'll complete a user experience survey as well. And in terms of really understanding the virologic prediction model, the dashboard study is going to be very important there because we don't really have a lot of good ideas about exactly how people make decisions using the output of AI models. And we know this has been a challenge in high-income countries like the US, with even radiologists with fairly sophisticated models being unclear sometimes how to weigh that model in their decision-making. There really is very little data from low-income settings or low-middle-income settings on this. And so we're looking at which models to display, whether they should be color-coded, and also what clinical supporting information is needed so that we can try to help people make better decisions. And one of the feedback from the qualitative research study was the clinicians were really interested in using these kind of things, different kinds of models, but they were really concerned that their own clinical experience would somehow be discounted in the process. And clearly that's not something we want to do. This is an example of the dashboard. We've been working on different user interface designs, and we're going to be modeling the new versions that are going to be tested in the qualitative research study very shortly. And so then in terms of the way we use information, we're going to be sharing and disseminating these models. If for anybody who's interested, the AMPATH research data set itself is available to qualified research groups. All the models, EHR components, and UI designs will be shared as OpenRS software modules and UI implementations. And we're looking at other data sources and algorithms to improve performance for the models as well. But of course, there's a really critical need for evaluation studies. This is just briefly mentioned. This is a study previously carried out in both Mozambique and Nigeria, looking at this question of missed visits and showing that there's quite a big difference in performance trying to take one model from Mozambique to Nigeria, for example. And I'll briefly mention that we've been doing a systematic review, looking for examples of machine learning based clinical decision support in low-income countries where there's actually been a clinical evaluation study. And I have to say that it's been really hard to find anything. This was an early version we did, in which we presented at the Global Digital Health Forum. We only found a handful of studies that even partially qualified. We've been looking at those cases where there's a study carried out in a lower middle income country. It has to be a machine learning model in actual clinical use and have a measure of clinical impact. And these are really the only two we found recently in the last time we ran the study. One is actually, ironically, from a colleague at Brown University, looking at prediction of diarrheal etiology in children, whether it was viral or bacterial. And then another study in South Africa looking at selection of drugs for drug-resistant TB, which is not actually fully reported yet. And then there were 3 other studies that were really prospective observational studies. So really very little evidence at the moment. This is an example of the diarrheal disease model. And one thing that came out of this was it was a good randomized controlled trial, both in Bangladesh and in Mali. Clinicians used the system on a mobile app, but it didn't actually change care. And we think from the initial further analysis was that the results of the models were presented really as a probability, and people weren't too sure how to use that in all cases. Anyway, so just overall, very disappointing number of studies and a real concern that we're not actually collecting the kind of data we need to understand whether these models are effective or successful. And so finally, just I think, we obviously need to have very high quality clinical data, and with systems that are open enough to allow us to really understand how the data is collected and how it's exported, and to be able to add machine learning components to the systems, and also look at different kinds of workflow across different and very heterogeneous clinical environments. And I think one key part of the study has been tracking very closely what actually happens in the field, and how many patients are actually being called and followed up and so on. Okay, I know we're a little short for time, so I will leave it at that. And these are my collaborators at Brown University and also in Moore University in Ampath.
Thank you, Hamish. That was a fascinating talk, and I think it illustrated really well kind of the theme of our conference around this second knowledge revolution, and how in some ways with the open MRS infrastructure, both in people and technology, you've been able to advance that in LMIC, sometimes in a way which is more advanced than developed countries. So I think that's really fascinating. We've had a few questions in the chat, so we've got a few minutes to take those now, if that's all right, Hamish.
Okay. Of course, absolutely.
So the first one from Dwayne Stewart. The measurements of physiologic parameters have a risk of being proxy measures for the psychological determinants of patient compliance. What is the outlook for incorporation of individualized patient health preferences as potentially more direct measures of patient attitude and compliance prediction?
It's a great question.
It's a long question.
But it's a really good question.
It's a very good question,
So,
yes.
yes, I mean, some of these things we're recording are clearly proxies for why people don't arrive. And I mean, I think there's a number of different areas where you can look at that. And one is really based on the work of Paul Farmer and colleagues at Partners in Health, looking at patients in Haiti and the number of small barriers that are to us maybe invisible, but which become really, like an absolute cliff trying to get to the clinic. People have no money for transport, or they have no one to look after their kids, or they have no one to look after a farm. And there's so many ways in which people can be disrupted in their ability to come to a clinic. So those are really important pieces. But also, yes, compliance is something that is a personal decision in many cases. So we have to kind of separate those out. And so I think we see more of the the barriers then necessarily patients choosing not to be treated or
Mm.
treating not to take the medications. But there are reasons why that might be the case. They might be feeling unwell with the medication, or they might be concerned about people seeing them take the medication,
Mm.
or they might have, uncertainties about the safety in some way. So compliance, requires a partnership between the patient and the clinicians. And I think that's a key piece of this.
Yeah, thank you. Second question, this is from Paulina in Utah. In your data set, is it possible that people are seen in other clinics which are not part of your data set? And if so, how do you deal with this type of missingness?
So we're kind of fortunate in AMPATH because there's a big catchment area which is nearly all supported by the same central organization and the same cloud-based EHR infrastructure, which is based in Moore University. So it's cloud-based, but it's not like, in the Amazon cloud. It's a local
It's a safe
system
one.
that's run within Kenya and supported by Kenyan, you know, organizations. Um, there are some cases where, yes, the patients may transfer to a nearby clinic that's not in this network. They might use Kenya EMR, which is the government-run system, which is also OpenMRS, but not the same system in terms of data storage. So by and large, we've been able to manage that because of the fact that such a large proportion of the patients are in one geographical area.
Mm. Great. Thank you. Question from Jeremy Wyatt. He thanks you
Hi,
for your
Jeremy.
talk. So you mentioned that your missed visit model had a good discrimination of 0.76. However, with so many variables, wonders how well calibrated the model is. How accurate are the risk predictions? For example, do 50% of the people who the model predicts will miss their appointment with a probability of 50% actually miss them? And suggesting that reducing the number of variables will improve the calibration.
So it's been a bit up and down, to be honest,
Hmm.
because initially when Alan was doing the original training on the research data set, he had more than 50 variables in the model. And then as we worked with that, you know, he was able to come up with a model which was much simpler. We were only about 20 or variables, and I think ultimately we've got 27 variables in the model we're using at the moment. So yes, I mean that was definitely, I think, a move in the right direction. And so, for example, the model I showed briefly about the one that was used in Mozambique and Nigeria, they had, I think, 70 or more variables in that model. And so I think that there's definitely concerns about overfitting. On the other hand, it's if you're too few variables, you also might lose some of the ability to understand what's actually happening in different areas. So I think it's a reasonable compromise. My personal concern is that we just not have high enough sensitivity. So I think that there are things going on, and maybe this relates to your previous questions, that we aren't able to identify, just by using the model based on the current data we have, as to why certain patients don't come. And even when the model is correctly calibrated, and we can get up to about 50% sensitivity, but that still means that we're missing a lot of people. So I think that there's bigger fish to fry, unfortunately, in this one at the moment. But some of the other studies have used GIS data to more detailed information about travel times from clinics, and there may be other social information and possibly even weather information that would be important. So, you know, one of the key things about the whole use of this model in this way is it's really about resource allocation, right? It's not actually about it's changing the care of certain patients by focusing attention on those most likely to miss their visits, but it's not really it's not doing something new. It's just trying to organize the resources a little bit. And the difference is going to be much more stark when we come to the viral load data, because there a negative result might lead to negative effects on patient care. So there's another whole piece here that we haven't quite fully got into yet.
Great. Thank you, Hamish. Um, one question I just wanted to put in myself. I was
Sure.
fascinated to hear about your SEAL data dictionary. I
Mhm.
wondered to what extent, because that is in itself a piece of computable knowledge. Um, to what extent is that tied into the OpenMRS platform, and is there potential for that knowledge base to be used elsewhere in other kinds of platform?
So it is used elsewhere actually, and there's been a lot of work recently to make there's the thing called the Open Concept Lab, which allows people to download sections of the data set and of the different mappings for a particular application. And so you can do that automatically within OpenMRS through a certain module, but it's also something that is accessible to other systems. And so these are pro bono mappings. They're quite large scale. So we have a very
Mm.
wide range of kinds of data mapped into the system, probably much more than we currently use in terms of all the different diagnostic areas. But Digital Square is an organization that Path has been supporting for a number of years, and there's a set of more than 40 open source different software systems used in global health,
Mhm.
and all of those systems have to have certain standards in terms of open standards and open software and so on. And a number of those systems can share vocabulary. So DHIS2 has been sharing some of the vocabularies for national reporting systems and so on. So there is definitely some flexibility in that area as well.
Mm. Brilliant. Very good. Thank you very much, Hamish. Very pleased to hear from you today, and it's brilliant to see how things are progressing in some of the lower middle income countries. So thank you so much, Hamish.